Now we've looked at numbers written in polar form, so that's z equals r bracket cos theta plus I sine theta. What we have to be able to do is do numerical operations involving these, particularly multiplication. Now, if we're able to multiply two polar form numbers together, so two complex numbers written in polar form, multiply them together, what that also opens up the door to is allowing us to do division, and I'll show you how that comes into play in a minute. But first we have to understand what happens when we multiply two numbers together written in polar form, but also, is there a quicker way to do it? Let's imagine that I have two numbers written in polar form. Now remember, that's z equals r cos theta plus I sine theta. Let's imagine if I give you two numbers, z1, which is a cos a plus I sine a, and z2, which is b cos b plus I sine b. Let's see what happens if we multiply the two of them together. So if I was to do z1 times z2, what that would then give me is a bracket cos a plus I sine a multiplied by b times cos b plus I sine b. What I can then do is treat this as I normally would and multiply out the brackets together. I'll keep the a and the b outside the bracket together with each other. So I've got ab, and then I'll have inside the bracket cos a cos b plus I times cos a sine b. Then I'd have the inner bits together. So I'd then have I sine a cos b. And then the last part, I squared sine a sine b. So that looks like a great fun expression. So what I'm going to try and do is see what ways I can simplify it. Well, I squared, I know, is negative 1. So I've got that there. So I've got minus 1 sine a sine b. So I've got a couple of real parts and a couple of imaginary parts. So let's see if grouping them together actually helps. So again, keep the AB out there. So if I group the real parts together, I get cos A cos B, take away sine A sine B, and then put the imaginary parts together, and I get plus I bracket sine A cos B plus cos A sine b. So I've grouped the two parts together. I've got my sines and my causes together. Now I need to figure out how I can simplify that down. Well, think back to your trig identities. Cos A cos B minus sine A sine B, that's the equivalent of saying cos of A plus B. Sine A cos B plus cos A sine B, that's the equivalent of saying sine of A plus B. So I can rewrite this as equal to AB times cos of A plus B, put that whole thing in a bracket, plus I times sine of A plus B. So what I'm able to do is simplify it and shorthand it down. Rather than having to go through this whole process every single time, if I'm asked to multiply two complex numbers together, I can use this format here. So z1 times z2 equals ab cos of A plus B plus I sine A plus B. Let's imagine then we'll extend that to division. Let's imagine if I had 1 over z. What would I get if I calculated that? So in this case, let's imagine we'll keep z in polar form in our standard polar forms. Let's say, just for argument's sake for this one, z is equal to r bracket cos theta plus I sine theta. Alright, put this together, we get 1 over r cos theta plus I sine theta. Now, think back to when we did operations with complex numbers. We didn't like imaginary numbers on the bottom. So what we had to do was somehow get rid of this. And in order to do that, we multiplied the top and the bottom by the complex conjugate of what we were after. Now, key thing to note, we're not going to worry about the r. The r is just a constant number. It's just a constant coefficient. We can leave that over there on its own. So we're going to multiply top and the bottom by cos theta minus I sine theta on both the top and the bottom. So cos theta minus I sine theta there as well. So what that then allows me to do is take this and simplify it, and I'll have cos theta take away I sine theta on the top over cos theta plus I sine theta times cos theta minus I sine theta on the bottom in my denominator. I've also got 1 over r here, because I'm just going to separate the constant 1 over r onto its own fraction there. Now, if I was to then multiply this out, so cos theta plus I sine theta times that, remember, a squared minus b squared is equal to a plus b, a minus b. And in this case, for this one here, my a is cos theta, and my b is the I sine theta. So I'd have cos squared theta minus I sine theta all squared. So the sine theta squared would just become sine squared theta. The I squared would become minus 1. So I'd get cos squared theta plus sine squared theta, which everybody in their right mind should know is equal to 1. So the whole bottom of this fraction disappears. And what I then end up with is 1 over r cos theta minus I sine theta. So that's what happens if I calculate 1 over r here. Now, we're thinking to ourselves, well, I said this was all about multiplication. Why are you bringing division into play? One of the reasons is if I was to ask you to do z1 over z2 using the format we had before, the way we would write this is we'd write it as z1 times 1 over z2. And if we were to write it like that and then combine it together using this rule here and the previous rule we'd covered, so the previous shorthand that we'd covered, what I'd be able to do is write it as a over b bracket cos of a minus b plus I sine of a minus b. So I'd be able to very quickly and efficiently get it to that format there. So again, a nice wee quick cheeky simple formula for us to be able to do it and multiply two complex numbers together, but in this case when one of them is 1 over, i.e. essentially dividing two complex numbers. Now what this allows me to do is come up with a couple of key points and a key bits of information that we can make ourselves aware of, and it will help us with some calculations that we're going to do when we're working with complex numbers in the polar form. First thing comes from what we just did. We noticed that the modulus of z1 times z2 is the equivalent of the modulus of z1 times the modulus of z2, and the argument of z1 times z2 is the equivalent of the argument of z1 times the argument of z2. So essentially splitting them off that way. Second key thing to note is if we take the complex number z equals r cos theta plus r I sine theta and we multiply that by cos a plus I sine a, this will give us something in the format r bracket cos theta plus a plus I sine theta plus a. Now what this represents is taking the vector representation of z, so from the origin to the point, and rotating it the angle of a in radians in a clockwise direction within our plane. So essentially you pin the vector down at the origin and you rotate it round by whatever the size of that angle is in radians. Now this comes in handy when we look at multiple solutions within our set of complex numbers that we're working with. This will be something we'll build on a little bit later. Third thing to note if z equals r cos theta plus I sin theta, and we calculate 1 over z, what we can then do is use the same logic from before, and it tells us that the modulus of 1 over z is the equivalent of 1 over the modulus of z's, and the argument of 1 over z is the equivalent of the negative argument of z. Now that seems a little bit counterintuitive. Why not 1 over the argument of z? Well, this comes about from the fact when we calculate 1 over z, we end up with a negative. So it's cos theta minus I sin theta for it. So it's because of that negative, it flips the sign rather than keeps it the same. What we've got here is we've got z1 over z2. We know that that equals a over b cos of a minus b plus I sin of a minus b from the previous work we've done there. What this also lets me see is something similar to before. The modulus of z1 over z2 is the equivalent of the modulus of z1 divided by the modulus of z2, and the argument of z1 over z2 equals the argument of z1 minus the argument of z2. Oh, now that's a lot of information to throw at you and a lot of different identities, and you're probably saying, well, why bother? What are they going to be used for? Well, I'm going to show you an example of a question just now and how they can come in handy and help our lives a little bit. Let's imagine I've got two complex numbers, z1 and z2, written in polar form. I've got z1 equals 3 bracket cos 30 plus I sin 30, z2 is 4 bracket cos 60 plus I sin 60, and I want to calculate z1, z2 and z1 over z2. This is where remembering those identities comes in handy. We know that z1, z2 is given by ab bracket cos of a plus b plus I times the sine of a plus b. Now for this, we just identify the wee a and wee b and our big A and big B, and we can stick it all together. So my wee a is with the z1, which is 3, my wee b is with the z2, which is 4, so 3 4s are 12, so it's going to be 12 times bracket cos of a plus b, a is the 30, b is the 60, so that's going to be cos of 90 plus I sin 90. Now if it wants you to leave it in polar form, just leave it like that. If it wants you to continue going on with this and make it as simple as possible, calculate each of these. So cos of 90, well that's 0, sine of 90 is 1, write it in simplest format, and I'd end up with 12i. So just be careful of where it wants you to take it to. If it wants you to leave it in polar form, leave it at this stage here. Taking it beyond, go to 12i. Next question was z1 over z2. Well, remember that z1 over z2 was given by the a over b bracket cos of a minus b plus I times sine of a minus b. So again, got to identify each of the parts and substitute them in. Well, none of them are going to change. My wee a, my wee b, my big A, my big B, they're going to be the same as they were in the previous example because it's the same two numbers we're working with. So a over b is going to be 3 over 4. It's then going to be cos of a minus b. A is 30, b is 60, so it's 30 take away 60, so it's going to be cos of negative 30 plus I times the sine of negative 30. So this is where thinking about how the values of our trig functions relate to each other. So cos of negative 30, what is that the equivalent of? Well, cos of negative 30, because of the shape of the cosine graph, is the equivalent of cos 30. And we know that cos 30 is a half. So that's then going to be 3 over 4 times a half. We've then got I sine of negative 30. Well, sine of negative 30 is the equivalent of the negative sine of 30. And sine of 30 is equal to negative root 3 over 2. So that would then be take away root 3 over 2 times I. So that would be it in standard form. If it wanted us to simplify it from here and put it in polar form, we'd use the same sort of logic, but we'd write it as 3/4 bracket cos 30, because we know cos of negative 30 is the equivalent of that, and then it would be minus I sine 30. Again, following on from the logic to here. So there you go, working with those two operations and all the different key characteristics and key points that we mentioned before allows me to do these sorts of calculations a lot quicker, a lot easier, and a lot more efficient. Just remember that last step. Make sure you leave it in the format they want, and you follow that through.